Our fellow students, I highly appreciate your attendance this time. This is one of the lecture series entitled with Fundamentals of Green Engineering. Uh, my contribution this time is subtitled with environmental problems can be likened to social dilemma games. Yes, my name is Jun Tanimoto. Yes, Professor Tanimoto. Let me turn off my video, image this time to enlarge the slide with the full scale. Okay. Um, what should I do? Oh, yes, this one. Okay. Uh, Let me start with my self-introduction. Yes, this is my personal information. Of course, I am working as a university professor, but at the same time, I have been active as novelist, especially dealing with romantic stories. And also that have been active as a painter, especially concerned on watercolor. Those two are, of course, the right business for me, but that those are quite important for me to stand up a university professors at a classroom to share something with youth generation, including you. Yes, just because all of those three, painting, writing novels, and research in the university, all are creative activities. Um, yes, aside from the and such a funny story about myself, my research concern is what you could see on this particular slide. My original background was building physics. Before I obtaining my PhD degree, I studied about what is called hydrothermal problems within building material, which is one of the central issues in traditional building physics. More than 20 years ago, I moved to KU. At that time, I shifted my expertise a bit from building physics to urban climatology. This shifting implies that the spatial scale of the objectives was a bit, how should I say, would be larger from the building scale to urban scale. And also, more than 10 years ago, almost 15 years ago, one day I perceived that all of my expertise, including building physics and urban climatology, which are categorized under the name of so-called environmental problem. Uh, it is deeply relating to what is called the social dilemma. So then, this is inception made me very aware about the what is called complexity science, including evolutionary game theory, applied mathematics, network science, and other stuffs relating to yes, statistical physics as well as mathematics. Uh, yes, in a world of complex system, in a real world, uh, which is very diverse, and the environmental problem cannot be contained within a single and simple system within an environmental system, a part of environmental system. But also you have to pay attention, you have to pay concern on the relation with human sector, as well as the social system, which is the entire system in which many human beings existing. Yes. So then yes, I invented the new word, what is called, yes, human environment social system, in which we should study, we should consider, we should account not only environmental system as physical system, but also human system as well as social system. Then as a whole, we have to treat this system into one single model. That is the basic concept of human environmental social system. Just let us start with our environmental sector. Uh, in a world of environmental system, as I said, which is the part of a physical system, which is still diverse. As long as our environmental system is concerned, there are so many diverse spatial scales, as you could see here, starting from uh, micro scale, human scale, indoor scale, via building scale, building block scale, urban scale, up to global scale. So then you have to pay attention not only a single spatial scale, but also neighboring, relating the spatial scales. When you are concerned, primarily concerned on indoor scale, you have to be aware of the spatial scales of the building scale as well as the human scale. And you have to model that not only indoor scale issues as a physical system, but also you have to consider connections with building scale events as well as the connection with human scale issue. Yes, that is a simultaneous the modeling, that concept of simultaneous modeling. Yes. Yes, mutually interactive view of over wide spatial scales is quite tough job, just because if you have the different, I mean, spheres with different spatial scales, it inevitably entails you to consider different time scale. To this end, you have a very tough situation when you go through what is called a numerical process, in which you do need time integral for different the spheres, yes, having different spatial scales, having different time scales. Just because if you consider, if you quantify by the time integral, you have to adjust all the spheres, all the time scales of all the spheres to the time scale, the smallest the time scale, yes, which requires you a huge amount of a computation, which is very tough. Even nowadays, you utilize the supercomputer system. It is still very tough job for you to get the meaningful numerical solution. Yes, this is one of the examples that we have studied for last 2 decades. This is very superficial schematic visual explanation about our urban climate origin model that we invented many years ago, which is called revised AUSSSM, revised artificial urban soil simultaneous simulation system, in which we paid the multi-scale issues. Not only we are concerned on building scale, but also urban atmospheric scale the events, and also very micro scale events concerning the how much the vegetation contributes to mitigate urban environment by the evaporation cooling effect and so forth. This is just an example. If you were interested in this thing, revised AUSSSM, you can visit our website. where you can find some publication. You can find the list of the publications. Some of those carefully deliver the detailed information about this particular model. Please visit our website. Okay, as I said, yes, our environment, the human social system as a concept is very tough job, just because there are three different spheres: environment, social, and human systems, right? Uh, of course, each of them would be possible to build up specific models for each of those three sectors. But more importantly, there is a fundamental question of how we are able to connect those two different spheres: environment system, human system, and social systems. Yes, which can be said some sort of a bridge connecting those three different spheres. What I would thought as a meaningful solution is that the game theory, or let's say the evolutionary game theory is able to dedicate building a certain solid village connecting those three different sectors, okay, spheres. What is a game theory? Have you ever heard the term of game theory? Perhaps yes, you do, yes. The game theory is applied mathematics. New applied mathematics emerged in the middle of 20th century, of which inception was funded by John von Neumann and Oscar Morgenstern. Their milestone work of which the title is Theory of Game Theory and Economic Behavior, published in 1944. In a word, game theory can be explained, can be paraphrased as below. Yes, game theory is a very good template to model human decision-making process. Yes. After this particular inception by those outstanding scientists in the middle of the 20th century, evolutionary game theory was growing rapidly in the 20th century. In fact, perhaps some of you know very well, there have been several Nobel Prize winners in the field of game theory. The most most outstanding, impressive professor, scientist, as the Nobel Prize winner concerning game theory was John Nash, yes, who were given Nobel Prize of Economy back in, as you could see here, 1980s perhaps. Yeah. Yes, and perhaps you remember the one Hollywood movie entitled with Beautiful Mind, which told a wonderful story about Professor John Nash. Yes, and the game theory can be applied the various fields, not only economical science, but also information science, politics, of course, and biology, of course, and nowadays, physics. And I have heavily favored the term of social physics, This implies that the very application oriented time relating to evolutionary game theory based on physics mind, physics science. Yes. Let us start with yes, the simple story to let you understand what game theory is. Yes, of course, the game theory can be applied to a simple scenario such as chess or the Japanese chess or Japanese Ego and other arcade games or Nintendo games, even a Nintendo game. Just because in those literally the games. There are so many values at the phases of human decision making, right? So then the game theory can be applied to those actual real games. But at the same time, the game theory can be applied to a more scientific world. As I said before, yes, in fact, politics and economical science are very good, outstanding examples in which the game theory as well as evolutionary game theory have applied. Uh, Let me start with explain about some fundamental the terms about game theory. The first term is zero-sum game, or let's say, depending upon the situation, you could say constant sum game. This is very simple. Like chess, the game has, how should I say, literally zero sum, which implies that you have winner and at the same time you have loser. So then the sum of those two is always kept at zero, which is the definition of the term of zero-sum game. Vice versa, there is another opposing the idea, which is called non-zero sum game, or let's say non-constant sum game, which has a more wide variety of applications. In fact, many real-world events observed in the field of politics or economic activities, those can be modeled by the non-zero sum or non-constant sum games. All right, let us start with a very archetype template of a game, which is called two-player, two-strategy game, of which acronym abbreviation is 2x2 game, right? 2x2 game. One of the most well-known the term, even the people in the street knowing is Prisoner's Dilemma, which is one of the game classes of 2x2 game. Yes, the situation is very simple. Yes, as you could see, you have two players, agent one, agent two, and each of the agents is allowed to offer yes, only binary strategies, either cooperation C or defection D, right? So then the combination of all offers amid those two players are just four, right? So then the result of this game is summarized with four situations, right? Depending upon, yes, either agent one cooperating or defecting, besides agent two cooperating and defecting. Let us defined as the rule of a two-by-two game. When agent Y cooperating and agent 2 cooperating, the result should be called reward, of which abbreviation is labeled with R. So then, yes, the player 1, agent 1 is given R as a reward, yes, which is called the payoff, yes. Agent 1's payoff is R. And also, because of the offers mutually same, agent 2 is also given reward R. That is the first situation. Let us move to the second. When agent A defecting and agent 2 defecting as well, in this particular situation, both players are given punishment, of which abbreviation is P, right? PP, yes. So then the diagonal elements in the payoff matrix are fixed, R and P, right? Yes, the remaining two elements are below. When agent A defecting, whereas agent 2 cooperating. If that is the case, agent A is given T, temptation, whereas agent 2 is given succor. This situation is symmetric. So then when agent A cooperating and agent 2 defecting, agent A is given succor S, and agent 2 is given with T, temptation. This is a definition of the payoff matrix, which contains four variables, R, P, S, T. Okay, that is general information about the 2x2 game. Okay, this slide explains about the particular case. As I said, one of the four game classes in 2x2 game, which is called Prisoner's Dilemma. Here you could see one example of Prisoner's Dilemma, right? R is 5, P is 3, whereas T is 7, and S is 2, okay? Suppose if you are one of the two players, let's say you are agent 1, which offer, the either cooperation or defection, do you think you should offer? If you are one of the rational players, if you are confident, being a rational, a person, right? Of course, the answer is you have to offer D. You have to defect. Why? Well, let's see. If, yes, you are agent 1, okay? You are agent 1. And the first element appearing in each of the elements, this, and that, are your payoff, okay? Whereas the second figure, each of the second figures, 5, 1, 7, 3, are payoff your opponent, right? And you are agent 1. Let's suppose when your opponent cooperating, which offer you should take? That is obvious, just because you should compare 7 with 5. Of course, you should maximize your payoff. To this end, you must defect, as I said. The same question can be imposed to the following situation. When your game opponent defects, your forthcoming expected the payoff would be either 1 or 3. Which offer you should take? Of course, with no doubt, you defect. So then in both cases, right, irrespective to your opponent cooperating or defecting, you should take defection as 2 options. That is the solution of the prisoner's dilemma case, okay? And this solution in which you defect is also true for your opponent. To this end, what happened? At the end of the game, you're playing the game with your opponent. That's obvious. You defect and your opponent defect, just because your opponent is also rational as you. Yes, so then what is called a Nash equilibrium, that is You're defecting, your opponent is defecting. You are given 3, your opponent is given also 3, which is very ironical situation just because you and your opponent know that there is another it's a better situation than P, right? Than P, that is R, right? In which you cooperating and your opponent cooperating, which is better than the P. R is more than P. But if you are rational, you and your opponent are not able to take cooperation but defection. Yes, trapped with what is called dilemma. Okay, what is called dilemma. Making a long story short, okay, let me introduce 2 specific dilemma parameters. Yes, in the class of 2x2 game, the making a long story short, there are 2 subordinates in terms of social dilemma, numeric, the mathematical dilemma. Yes, that are gambling intending dilemma, which is yes, labeled with DZ, of which definition is the subtraction between T and R, T minus R. Okay, in this case, 7 minus 5 is equal to 2, which is positive. Yes, DZ is positive. The second, the subordinate dilemma is called risk averting dilemma. Yes, which is labeled with DR, which definition is P minus S is equal to, this case, of course, 2, which is positive as well. So then, in a case of prison's dilemma, DZ, both DZ and DR are both positive, which implies that in the case of prison's dilemma, both subordinate dilemmas, yes, DZ and DR are existing. Yes. All right. This slide, yes, intends to explain what I just mentioned. Yes, Nash equilibrium means that if you and your game opponent are both rational, what's happened, what is the consequence of the game? Yes, as I explained, that is P, in which you're defecting, your opponent defecting also. Yes, P situation. Yes, in this case, prison's dilemma brings you P as Nash equilibrium, which is the definition of the Nash equilibrium. Okay, whereas the term of equal palette optimum, yes, it means that yes, there is a much better situation than Nash equilibrium. Yes, where you are perfectly equal to your game opponent. For only you, yes, this situation is best for you. But for your game opponent, which is worst, right? The same situation is also true for your game opponent. But this situation, R, yes, equal palette optimum is despite the second best, you and your opponent are able to be given the better payoff than the Nash equilibrium. So the conclusion of this, the explanation, yes, if Nash equilibrium is not consistent with equal palette optimum, you have the dilemma. This is the Babel definition in terms of mathematics for existence of dilemma. If there is a social dilemma, there is inconsistency between Nash equilibrium and equal palette optimum. Okay, remember this proposition. Well, still we are in the prisoner serpent. This diagram shows each of the payoffs that you are able to be given. Yes, S, P, L, T. Just because you are ranking as a player one, and also y-axis, y coordinate implies the payoff of your game opponent player two, right? And here is P, and that is R. Those two are diagonal just because the payoffs of those two situations, P and R, are same for you and your game opponent. Yes, that's diagonal. Yes, appearing on the 45-degree oblique line here. Okay, whereas this here implies a T, which is the best solution for you and the worst solution for your game opponent, right? The vice versa here represents S, which implies the worst situation for you, whereas the best situation for your game opponent. So then, yes, the being 45-degree oblique line, T and S are mutually symmetric. Okay, mutually symmetric. And back into the definition of dz and dl, this deviation between t and l is dz. And also this deviation, geometric difference between s and p, represents dl. In this case, in the case of prisoner serpent math, as we confirmed in the previous slide, both dz and dl are positive. Okay, and again, here is equal Pareto optimum, right? This all implies the equal Pareto optimum. But ironically, natural equilibrium must appear P. Okay. The next class after PD, prisoner serpent math, is chicken, which is sometimes termed with hog and dog game by biologists or snowdrift game. Anyway, this is a bit specific. This is different from the prisoner's dilemma. Why this particular game class has been called the chicken comes from the another Hollywood movie, as you could see here, that is yes, titled with Rebel Without a Cause by James Dean back in 50s. Perhaps the most popular, one of the most popular Hollywood movies are in the generation of your grandmother and grandfather. This is a bit different from the PD situation. Look, the same diagram from the previous slide, but being different from PD. Chicken has positive DZ, whereas negative DL, okay, negative DL. So in this case, yes, the diagram is like this, and the important issue is, as I said, DZ, which can be said chicken tetragon is positive. So then in the chicken game, the class of the chicken game, there is a chicken tetragon. Whereas, yes, because of negative DL, you could say stack hunt type dilemma does not exist just because DL is negative. In some, chicken game has only chicken type dilemma, whereas stack hunt dilemma does not exist. Back into the previous slide, PD has both. PD has both chicken type dilemma and stack hunt type dilemma. Okay. Here you could see the example of the chicken. Yes, being different from the PD. What is the best? What is the best? Oh, no, the point of the what is the best is the same to PD, just because, yes, T is maximal, 7. The second best is also same to PD, that is R, right? The, the difference from TD is below, okay? The worst appears not S, but P. P is worst, whereas the second worst is S, which is different from the PD, okay? So then, the order of the elements appeared in the pair of matrix in the chicken game. T is maximal, R is second maximal, which is followed by S, which is second worst. The worst is P. Whereas in the case of a PD, best is T, the second best is all, the second worst is P, and worst is S. Okay? This is a point of the difference between PD and the chicken. To this end, yes, so back into the definitions for DZ and DL, as I explained in the previous slide, yes, in the case of the chicken, DZ is positive, whereas DL is negative. As I said, you can paraphrase with a paraphrase that in the case of the chicken, there is only chicken tetragramma, whereas there is none of the shadow of stack-hunt dilemma. Of course, what I have promised in my explanation is the chicken dilemma means gamble intending dilemma, whereas stack hunt dilemma is risk averting dilemma. Okay. Next is the stack hunt. Yes, the third game class after chicken is stack hunt dilemma, of which naming as a stack hunt dilemma was originated from a very one of the most outstanding the classic the books relating to philosophy, modern philosophy, written by Jean-Jacques Rousseau, yeah, in perhaps the 17th century. Anyway, this is the diagram of stack-hunt dilemma. A bit different from the chicken, as well as a bit different from the PD, just because in this case, DZ is negative. So then you have the best situation to maximize your payoff, whereas DL is positive, right? That's why you could say that in the case of the stack hunt, as a third game class in 2x2 game, you only have stack hunt dilemma due to a positive DL, but you don't have chicken dilemma due to a negative DZ, right? This is example of stack hunt. Let us check out the order of 4 variables, PLST. The best is R, not T anymore, in the case of PD or in the case of the chicken. Yes, unlike the PD and chicken, R is best. The second best is T. Yes, T follows to R. The second worst is P. The worst is S. So then R, T, P, S. That's quite different from the previous 2 game classes. To this end, we can quantify that as I explained in the previous slide. DZ is negative, whereas DL is positive, which can be paraphrased that you don't have chicken dilemma, but you have stack hunt dilemma. Okay, this is the third game class. The fourth game class is trivial game, which does not have any social dilemma whatsoever. So then, in other words, trivial game can be said dilemma-free game as a class, which diagram is quite different from the previous three game classes, just because DZ is negative and DL is negative as well. So then you could see immediately what is the best situation that is R, and what is the worst situation, which is obviously P. This is an example of a payoff matrix of a trivium game, right? Please confirm that carefully and deliberately. In this case, the R is best, the T is second best, and the second worst is S, and the worst is P. Yes, noting, confirming this point, when we quantify DZ and DL, yes, you could see as here, yes, DZ is negative and DL is negative. So that the trivial game does not have any of those two subordinates, chicken dilemma and the second dilemma. Yes, the trivial game does not have chicken dilemma and also does not have second dilemma. So those are all the four game classes in the 2x2 game. Let us summarize, okay? Why 2x2 game is what I explained at the beginning. Yes, 2x2 game is very fundamental and very typical and effective as a template to quantify the real social dilemma context, right? In which only two player and two strategy, right? So in the world of 2x2 game, there are four game classes as well: prison dilemma, pity, chicken, stuck hunt, and trivial game, right? And more precisely, PD has four subordinate dilemmas: chicken dilemma and stuck hunt dilemma. Whereas, meanwhile, the chicken game has only chicken dilemma, does not have stuck hunt dilemma. The stuck hunt has only stuck hunt dilemma, but not with the chicken dilemma. To this end, trivial game does not have any of those two subordinate dilemmas. That's the point. That's the all about, yes, from theoretical background about 2x2 games, right? Which is quite powerful and how should I say, very fundamental to discuss about game theory and evolutionary game theory. All right. Let me put this. What I have told so far is about the game theory. From now on, I'd like to move to evolutionary game theory. What is the difference from the game theory when you say the evolutionary game theory? Of course, the term evolutionary means the time evolution, with no doubt. Time evolution. What is a time evolution? Okay. Although I explained in the world of 2x2 game, there are two players. Two players. Yes, that's very true. Okay. In the battlefield of the game, certainly there are only two players, you and your opponent. But behind those two players, there are so many, yes, potential players. More precisely, the number of potential players are millions, or let's say infinite. Yes, that is quite important point. Quite important point. There are so many infinite the players, and those players are yes, are million, of course, and then you are the referee, or let's say you are God, all right? to handle the procedure of our game, the sequence of the games, okay, evolutionary game, right? You are God, and you pick up randomly, you randomly pick up two of the players from the population, which is infinite, like this. And the one is that happen to be cooperator and happen to be defector, and they are given the payoffs right there. And you should call all of the remaining players so as to give the payoffs right there, right? So then all the players, which is infinite, all the players are given the payoff, right? At this time instance, right? Uh, like 0, 1, 1 plus dz and dl. Oh, let me put this. In the slides so far, yeah, when we say payoff matrix of the 2x2 game, R, T, S, and P are defined, but this time without the loss of the generality. When we fix R of 1 and P of 0, right, and back into the definition of dz and dl, yes, the definition of mathematics, T can be parameterized with 1 plus dz, whereas S can be, yes, quantified with minus dl. So in the previous representation of the payoff matrix, you have 4 variables, P, L, S, T, whereas now you have only 2 parameters, only dz and dl, which is quite convenient for you from mathematics point of view. Yes, please remember this point. And now, back into the central story of what I explained. Okay, all the players are given the payoffs like that. And after completing all the games, each of the players is allowed to refresh his or her strategy, right? Either keeping C, either keeping D, or shifting to D to C or C to R, right? Depending upon how much each of them are being given as a payoff, right? If he feels dissatisfaction just because what he is given as a payoff is less than the average, the social average, he would be dissatisfied. So then he has a very strong incentive to shift his strategy, right, from C to D or vice versa and so forth. And of course, in the case of a PD, this is a PD, right? This is a PD, which implies that, yes, please look at here, right? DZ is positive and DL is positive as well. This is PD, right? And take a look. And this guy happened to be, fortunately, play with another cooperator as a game operator, game opponent, sorry. Whereas this guy played with defector. That's fine. Yes, minus dz is given. He is imposed to dl, the dl, right? And which is which is the smallest, right? Which is the smallest. Whereas the defector, for instance, this guy is willing to have, enjoying to have 1 plus dz, which is maximum payoff, right? So then for them, yes, defection is advantageous, obviously, just because PD, just because dz is positive and dl is positive. So then if the initial, the state of the society, right, in which the 50% of the all agents, infinite number of agents are cooperator and compulsory are defectors, right? 50% of the cooperator. And if you draw the cooperation fraction, the fraction of the cooperators, starting from 0.5, yes, the the fraction of corporator decreases rapidly just because the key thing the corporation as a strategy is nonsense for them. Yes, just because they are suffered from a very small payoff. So then if there is a concept of the time evolution in the case of the PD, right? The fraction of that corporator decreases, right? That to descend, what's happening is all the vectors stage appears like that. Have you understood? Okay. Yes, this is the explanation of the evolutionary game theory. Yes, which is consistent with natural equilibrium, right? You remember that in the case of the PD, natural equilibrium is P, yes, mutual defection, which implies all defective situation, all defective situation. Yes, this is the explanation of evolutionary game theory as a concept, right? Have you understood? Have you followed what I have explained? Okay. Yes, but for this explanation, there is a quite important the premise, which is twofold. Yes, one is all potential players are well mixed, and infinite. Okay, well mixed and infinite is the quite important premise for this explanation. What is well mixed? What is well mixed? Okay, that's quite important thing if it comes to the evolutionary game theory. Well, so our antonym to well mixed is social viscosity. Social viscosity. Social viscosity means that not well mixed situation. Well, or in other words, you can say that you can paraphrase the term of well mixed to be totally anonymous situation. Totally anonymous. Totally anonymous. What is anonymous? Of course, it implies that you don't know about your game opponent whatsoever. You don't know. You don't have any information about your game opponent. All right? That is the definition of well mixed. You don't know about the game opponent. Right? Antonym to this situation. Antonym to the situation of well mixed. Antonym to the situation of anonymous. Anonymous situation is, yes, the situation in which you know something about your game opponent, which can be termed with social viscosity, just because you are able to obtain a certain information about your game opponent, right? To making a long story short again, if you back to the previous situation, well mixed and infinite situation, right? And if it comes to the PD, the natural equilibrium is totally defection, all defective situation. But if you observe what's happening in nature, yes, the sphere of course, the human being, apes, monkeys, the lions, and other mammals, even the amphibians or the reptiles or even insects, you are able to obtain many proofs that some of those species are able to oppress the social dilemma situation, bringing the social harmony that is a social cooperation. It's a quite interesting and a mysterious question, which was originated by the Darwin in the 19th century. Okay. Yes, paraphrasing this, we can say that even if some of the species being exposed to prisoner's dilemma situation, they are able to solve prisoner's dilemma situation and obtaining certain extent of cooperation. reciprocity situation, right? The key, the answer to solve social dilemma, yes, could be classified into those following those 5 mechanisms, right? Uh, that was proved very recently, back in 2002, by Professor Martin Noak, working for Harvard University, right? Key interaction, direct reciprocity, indirect reciprocity, network reciprocity, group selection. Each of those 5 protocols, mechanisms, is able to add somewhat social viscosity to red system diverse from the well-mixed situation, totally anonymous situation, right? Let us pick up the example that is network reciprocity. Well, instead of well-mixed situation, yes, now you are connected. Also, your game opponent are connected by the social network, by a certain topology, like Lattice, Scalfly, Small World, Graph, and so forth. Anyway, you are only allowed to play game with your neighbors, right? In this case, this guy has only 3 neighbors. That is our simple definition of the network reciprocity. Just adding this mechanism to well-mixed situation. Interestingly, instead of the totally defective world, you are able to realize certain, yes, and this is what's happening in the case of a well-mixed situation. Yes, all defective situation. Whereas, if you have a social network, if you rely on network reciprocity mechanism, yes, in this situation, even starting from the half cooperator situation at the beginning, the cooperators are able to survive like that. Yes, this is a very good proof for some of the animal species are able to, how should I say, generate social system allowing the mutual cooperation reciprocity, right? Yes, this is a key point of the evolutionary game theory. And this particular slide schematically explains about each of those 5 protocols, right? Key interaction, direct reciprocity, indirect reciprocity, network reciprocity, and group selection. If you are interested in this, if you intend to know more profound information, knowledge about that, you are able to consult with some of my books published by Springer. If you visit to my website, you can get the information about those books, right, by the publisher, the Springer. Please buy it, one of those. And the most recent publication, most recent book was published in 2021 March, which is, I forgot the title of that particular book, the most recent book. Anyway, you are able to information about that publication. All right. So far, what we have presumed is that the players are only 2, you and your opponent, but we are easily extend the situation to a multiplayer situation. Okay, this is a very good template, which is called public goods game, which is classified to prisoner's dilemma. Yes, but not 2x2, but in players. Prisoner's dilemma. The story is very simple. You have the plural players, more than 2. In this case, in this example, you have 5 players, in which 2 defectors and 3 cooperators. And cooperators are requested to donate unity to public goods, right? Yes. and the stored resource to the public goods would be amplified by a certain external mechanism. Say, in this case, yes, the resource is multiplied with R, so then the 3R is the flute, right, of the public goods. And this 3R is now equally distributed to all the participants to the game, irrespective to a corporator or a defector. So this situation can be quantified with this simple equation, pi c and pi d. Pi c means the payoff function of a corporator, and the pi d means that for defectors. And if you draw pi c, pi d as a line graph, along with corporator's fraction that ranges from 0 to 1, 0 means, of course, the all defector situation, whereas 1 implies the all corporator situation. dz, which is represented by red line, is always above, than the that of corporator, pi c, right? Which implies that, yes, now, instead of the line, you have the dot, red and blue, red and blue, red and blue. And the green line means the social average payoff, right? Obviously, let me put this, yes. Yes, now you are here, and suppose you are one of the corporators. So your payoff being given to you is here, right? And what you could think is that what option should be taken for next time step, either corporation or defection? Of course, you think, if you are rational, instead of offering corporation, you defect just because, yes, defector's expected payoff is rather than that of corporator. So then you shift from corporation to defection. The same thing is true for all participants in the population. So then what's happening as a social dynamics is that, yes, the fraction of the corporator is gradually decreasing that way to this end as a natural equilibrium. Yes, you attain here, which is all defected situation. All defected situation. Ironically, what is the social maximum, social optimum is, yes, here, appears here. Just because, take a look on the green line, as I said, which implies the social payoff, right? Where is the social maximum appears? With no doubt, that is a situation where all participants, all population cooperates, right? The all cooperators situation. So in this public goods game, yes, equal Pareto optimum, maximum social payoff situation appears all cooperators state here, whereas natural equilibrium is all defectors situation. Obviously, those two are mutually different. That's why, yes, there is a dilemma, social dilemma situation, especially in this case, public goods game can be classified to prisoner's dilemma. Why prisoner's dilemma? Okay, that can be evaluated by the geometric relation between, yes, red line that implies pi d and blue line that represents corporators payoff. Okay, if the red line is always above than the blue line, you can say the game can be classified to prisoner's dilemma, right? D dominates means that the natural equilibrium appears on all defected situation. Take a look here, yes, opposing to that, if the green right, sorry, blue line appears always above the red line, yes, which is called trivial game. It, in other words, C dominate just because it's a social dynamics. Social dynamics. The fraction of the cooperator grudges increases, 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 increases. So then, to this end, classical equilibrium is totally consistent with, yes, social optimum situation, right? That is the explanation about, yes, multiplayer trivial game. The check-in is a bit different because, yes, red line crosses with the blue line, right? Red line crosses with the blue line in the intermediate cooperation fraction. But take a look carefully, yes. In the upper part, no, it's not so good way to explain. In the region of more cooperators, the red line is above the blue line. In this case, social dynamics leads to the following situation. If you start from the relatively cooperative situation as a whole of society, the cooperation fraction decreases. Whereas if you start from the meager cooperative situation, yes, the fraction of the cooperator increases like that. So then the national equilibrium appears in the middle course of 0 up to 1. Yes, that is the chicken game. Whereas a stack hunt game is, yes, still analogous to chicken, but quite different, just because in the region of more cooperative, yes, blue line is aloft than, above than the red line. That's the quite different. So then, starting from the relatively cooperative situation, the social dynamics increases social cooperation bit like that. To this end, yes, you see national equilibrium being consistent with the social optimum situation. There is, in a sense, a very happy situation for all the players. Whereas if you start from the meager cooperative situation, the social dynamics lets the cooperation fraction decrease bit and bit and bit and bit to this, and national equilibrium appears all defective state. Yes, that is the multiplayer second game. Yes, please remember this. Okay. From now on, yeah, I'd like to tell about the very rich story of the application of game theory and evolutionary game theory. Yes, to model quantitatively social dynamic context, right? Its application is diverse, very numerous, okay? Let's start with very simple caricature that relates to building physics. My original expertise, as I said, and urban chromatology. Yes, perhaps you have known there is a jargon in the field of urban chromatology that is heat iron. Yes, heat iron. The heat iron is very intensive during the summertime, just because outside air temperatures are inherently high, and also, I mean, exhausted heat from the artificial activities, from the buildings, from the vehicles or others, quite much. So then uh, the outside temperature in the urban area increases very much for last 100 years, right? Yes, this contains some sort of the dilemma because yes, suppose a foreign situation. You are inhabitant of in a certain indoor space, right? If you don't rely on cooling system, you feel quite hot just because the inside temperature is quite high. What you do, right? If you mitigate your indoor environment, you would rely on cooling system locally, then turning on your, the cooling system on. It brings you a very comfortable situation like that. But, but despite you being happy, you being comfortable, your helps exhausting the heat from the outside apparatus of the cooling system. Yes, like that. This exhausted heat helps to increase, yes, on outside air temperature in open area. Bit more, bit more, bit more. Yes, and this story is also true for other people. Then what's happened to this end? Perhaps most of the people are willing to or favor to rely on cooling system during the peak summertime. So then the huge amount of exhausted heat will be exhausted from the each of the apparatus. So then the outside air temperature in the other side increases significantly. So then the heat iron becomes much significant, right? Intensively, and this brings you a certain vicious circle, which implies that you must intensify the extent of cooling system energy consumption, just because yes, if the temperature of the other side increases significantly, yes, the cooling power, the cooling load requires more. Yes, this story contains a social diagram situation. The second story for the application, I'd like to share this interesting story that is, yes, a traffic system, traffic flow system. Yes, the road is some sort of resource for the drivers. Yes, but the amount of the resource of this particular resource road is limited, right? If you have so many vehicles try to occupy the road space, which implies that right, there's so many vehicles coming into our expressway, for example, right? Inevitably, to this end, you could be involved with a heavy traffic jam, right? And this traffic jam would be intensified by very egocentric activity of each of the individual drivers. If you want to travel faster than others, you may rely on frequent lane change like that. What this bring to you, that's okay. For you, it's very happy just because you are able to shorten your travel time. Yes, but at the same time, your behavior brings to the system as a whole is very cumbersome, troublesome, just because your behavior as a dynamics triggers the jam, traffic jam. So then if you behave egocentric way so as to maximize your own payoff, your own individual payoff, as a whole of society, all the people would be suffered. Yes. Also, this story contains the social dilemma situation. The third aspect, third actual application is, yes, what is called vaccination yang, which is very vivid and, how should I say, heavily concerned by all of you and nowadays in the wake of COVID-19. Yes, the question is whether you participate vaccination or not, right? So far so, the cost of the vaccination of the COVID-19 is basically free. as the government covers the vaccination, expense. But if it comes to the seasonal influenza digressing from the COVID-19, which is a compensatory basis, you have to pay certain amount of cost for the vaccination. And of course, if you back to the COVID-19 as well, the participating in the vaccination entails some sort of the risk for the health, right? You may be shocked with a certain side effect of the injection, the vaccination. That can be set a certain amount of the cost. Anyway, the participating the vaccination inevitably entails a cost, right? Yet, a society contains many people, not only you. There's so many people, right? As a story, it follows the following, right? For you, the best scenery for you is you are not intending to participate in vaccination, but rest of the people than you participate in vaccination. If that is the case, what is called herd immunity can establish, right? The most of the people in the society participating the vaccination brings the very low risk of pandemic in which communicable disease is not able to spread in the society through the complex social network, just because most of the people are protected by the immunity. In that sense, you are very, very happy just because you don't to pay any risk for vaccination, but you are enjoyable of infection free, right? And this story is very true for others than you. What's happened to this end is that all the people intend not to participate in the vaccination. Right, this is very tragic situation just because very less amount of the people are willing to participate in vaccination. Of course, herd immunity corrupts. This is no hope to establish the herd immunity. So then the breaker to the COVID-19 is inevitable, right? And this story also contains the social dynamic situation. All right, yeah. From the foreign time, I'd like to share some application, the result of the actual project in Abra that relates to the vaccination game. Yes. To analyze the vaccination game, we have to quantify how epidemic spreads in the society through the complex human network as a physical network, right? The connection between the people, right? Based on mathematical epidemiological model. Yes, that can be to quantify the theory of population, which is one of the very powerful the tools in the field of statistical physics. The population is heavily used the events in the real society. One good example is wildfire right there, wildfire, okay? And suppose you have the woods, right? The huge, very rich woods, and someone the fires. Someone triggers the wildfire at a certain point, right? And this wildfire spreads rapidly if the weather situation is very dry, right? And depending upon the situation, depending upon the season, depending upon the geometric the condition, a wildfire spreads very rapidly. So then the total area blown out is quite huge in some cases, as you know very well, which is very rare in this country, but is quite common in the States or Australia, those kind of the countries, right? The wildfire can be yes, the model with population, which is also able to be applied to the spread of disease, just because spreading the disease is quite analogous to the spread of the wildfire, right? In this context, committing vaccination, obtaining the immunity means like what this caricature depicting, right? That if you are participate vaccination, you one of the tree, one of the wood, is totally safe with very solid the barrier being given around you. Then you are totally free from the wildfire, the effect of the wildfire. You are able to survive despite all of the trees around you would be burned out by the wildfire. Yes, that is the situation of the population, and that is what the vaccination game models. Yes, the vaccination game is very complicated. So then, making a long story short, right? Yeah, in the supercomputer system, we build up our artificial society in which many agents that are human beings, of course, generated, and each of the agents has a decision-making process, right? Either committing vaccination or not committing vaccination. Yes, this is explaining what our model contains, the mathematical aspect, which contains mathematical epidemiology and evolutionary game theory. In other words, vaccination game is built up with dovetaling mathematical epidemiology with evolutionary game theory. If it comes to mathematical epidemiology, we especially adopted what is called SIR model, right? Yes, at the beginning of our simulation episode, each of the agent is asked to whether committing vaccination or not. If he or she commits the vaccination, he is requested to pay the vaccination cost. Yes. If it comes to payoff, it should be modeled with a negative value. That's why you could see minus CL. CL is a vaccination cost, right? If you don't commit, if you don't commit to vaccination, of course there is you are requested to pay the nothing, of course. If you commit to vaccination, you are okay in the season just because you are protected by the immunity brought by the vaccination. But if you're not, you are exposed to the risk, whether you would be infected or not, depending upon the stochastic process. If you are lucky, you are able to free ride. You are unlucky, you would be infected. In this case, you are requested to pay the maximum cost, that is the infection cost. Going through the normalization, the vaccination cost is defined 1. So then you could see -1. Yes. Of course, these are the vaccination cost is denoted with CL is less than 1. That is the story. And the season is repeated, and the social equilibrium can be solved in simulation, a bunch of the simulations done in the framework of our supercomputer system, right? With respect to our underlying social network, we are able to many barriers of topologies, ring, lattice, regular network, with a scale-free, with a small one, and so forth, whatever you like. Yes, this is animation of the disease spreading, and we have we have gone through many actual the projects. Well, one of the projects is the subsidy. Yes, to protect as a government to protect their own people from the risk of course, the COVID-19 over seasonal influenza and so forth. One good solution is providing the subsidy for the people to participate in vaccination, right? But of course, this kind of policy entails expense very much. Yes, just because, yes, the total cost of the vaccination for many people are quite huge. So then one idea is that the subsidy should be limited to certain people. For example, only senior people or socially weaker people, of course, including senior people as well as children or pregnant female and so forth, right? Just because the budget, the governmental budget is limited. The question is, if that is the case, whether it's a best policy to distribute subsidy exists or not, right? It's very useful the question to answer, yes. And we established the specific vaccination, so the model of the vaccination game for this case, and going through the huge amount of multi-agent simulation, we got some interesting result. Perhaps you know the idea of the have, right? Have. Have means HUV, which implies that an agent having many, yes, the huge number of neighbors, the friends, right? Whereas social fringe means like very isolated the people, like me. I don't have any friends around me. I'm very isolated, right? Just because all the people around me hate me. Yes. Aside from the joking, yes, have in the fringe, you understand, okay? And if we presume the underlying network, uh, uh, if we presume that the scale-free network for underlying network, there are hubs and also there are many fringes, right? The number of hubs is not so much, of course. If you see this, the degree distribution. Degree means the number of the neighbors of each of the agent has, right? Whereas the fringe people, the fraction of the number of the fringe people are quite much like that, right? And very like every policy that government is able to take is that the subsidy, or let's say the free ticket for the participating the vaccination, should be given to half of people. That can be said have priority policy, right? Do you understand? Have priority policy. That is very reasonable and very likely, just because how people are exposed to heavy risk of infection. So then, as the government rebel, to shut up those dangerous people in terms of the spreading the disease, the free ticket should be distributed to the heavy people. In fact, yes, through our huge amount of numerical experiments, right? I'd like to skip the remaining, this right, just because the remaining time is very limited now. Yes, Although I do not explain the detail how you see your all of those visual steps. Anyway, yes, this means that have priority policy, fringe priority policy of the brand policy, right? Yes, the making a wrong story and the simplifying what we have obtained, the final result in Word. Yes, the most of the cases, how priority policy is very powerful to minimize the social risk. Yes, to minimize the final epidemic size of the outbreak. But in some cases, interestingly, hub priority, priority policy is not able to be justified. That's quite novel finding in a sense. What condition would be? What condition uh, would be justified avoiding high priority policy? That is, yes, uh, ERA highlighted region. Yes, although I do not explain the detail, yes, but let me put x-axis in each of the panels means the CR, vaccination cost, ranging 0 up to 1. 0 means that the total flea vaccination cost, whereas 1 means that the vaccination cost is equal to the disease cost, right? And y-axis means the size of the budget the government is able to take for subsidy policy, right? If this maximum point comes to, it implies that government is able to free ticket to all of the people, right? Whereas the smaller y-axis value means that the governmental budget is limited, right? So this arrow triangle appears in the smaller vaccination cost and the smaller the governmental budget. Yes, if the situation is like that, with the smaller vaccination cost, with the smaller the governmental budget, yes, half agent policy is partially denied, partially denied. That's quite interesting. Why this happens is that, yes, if that is the case, the budget is very limited. The priority should be paid not to have people, but fringe people. Why? It's just because the half people are aware themselves that they are exposed to the potential jeopardy of the infection, then they themselves participate vaccination by paying themselves, right? By themselves, just because they are aware of the risk, right? So then, in this case, the ticket, the limited number of free ticket would not be distributed to half people, just because half people are able to aware the jeopardy and they how should I say yes consciously participate the vaccination, whereas fringe people are isolated. So then, yes, the free ticket rather should be distributed to the fringe people. Yes. Oh, the time is up. skip the remaining slides. This is assignment, right? To summarize what was delivered in this class, your summary must contain the following keyword: game theory, vaccination game. Of course, this class is delivered to you as a video, then you can repeat what I have just mentioned. You can repeat, and also you can visit my website, and also you can consult with my books as well as publications or other websites, and you can look at what game theory, evolutionary game theory means, what the vaccination game represents, all right? And please summarize what I have delivered this time. That's the first issue. As a second, describe an example of allocation of the game theory. Yes, our example of application of the games theory around your oven project, right? I have known that each of you attending this class would be very diverse in terms of expertise. But I do believe that to some extent, more or less, you have a certain example or examples in which the game theory or evolutionary game theory can be applied. And please think about that. Please consider, please account, please establish a certain situation of a project in which the game theory can be applied. Okay? You must report those two issues to me, directly to me by email. And the deadline is January 26th, 0 a.m., right? And the following information is quite important. The report should be in the PDF, yes, attached to your email, right? And you must add subject by describing assignment of fundamentals of green engineering. Yes, please remember this point, okay? Thank you very much for your attention this time. Thank you very much.